Hello everyone. Today we're going to explore the basic concepts of assembly language to understand how software communicates with hardware at a fundamental level. So, why should we learn assembly language? Think of assembly language as the bridge connecting human readable code with the raw binary instructions of machine code. When you work this close to the hardware, you gain an unmatched insight into how computers really operate, from the way memory is managed to the CPU's behavior. While today's developers often use high-level languages, knowing assembly gives you critical skills for system programming, reverse engineering, and getting peak performance in environments with limited resources, such as embedded systems. It is used for system programming tasks like writing OS kernels and drivers, for reverse engineering, for performance optimization, and in those embedded systems. So, learning assembly does more than teach you a language. It actually reshapes how you think about programming. It makes you a better programmer because you gain a much deeper understanding of memory, registers, and instructions. Programming languages exist at various levels of abstraction. High-level languages are designed to be human-readable and portable. Below this, assembly gives you direct hardware control. At the very bottom is machine code, which is the CPU executable binary format. Now let's discuss how data are represented in a computer. Computers use a binary system of zeros and ones to store and process all data. The smallest possible unit of data is a bit, and a collection of 8 bits makes 1 byte. Numbers are handled in a few ways. Unsigned integers can only be positive values, such as from 0 to 255, while signed integers use a method called 2's complement to store negative numbers. Floating point numbers are represented using binary scientific notation. Characters, on the other hand, are represented using standards like ASCII or Unicode. For example, in the ASCII standard, the capital letter A is equivalent to the decimal number 65, which is 0100000001 in 8-bit binary. The number 1 corresponds to decimal 49, or 001100001 in binary. Next, we'll touch on Boolean expressions, which we can break down into 3 parts: binary logic, truth tables, and Boolean functions. Binary logic is based on the idea that computers operate using binary values where 0 represents false and 1 represents true. The basic Boolean logic gates are AND, which is true only if both inputs are 1, or which is true if at least one input is 1, and NOT, which simply reverses the value. To visualize this, we use truth tables, which show the output of these Boolean operations for every possible combination of inputs. These concepts come together in Boolean functions. A Boolean function will take one or more binary inputs to produce a single binary output and is widely used in designing hardware circuits. With those basics covered, let's examine a specific example, the x86 processor architecture. Every CPU follows a continuous cycle to run instructions. First, it will fetch an instruction from memory. Second, it will decode that instruction to figure out what it means. Third, it will execute the action. Finally, there is an optional 4th step, store, where it saves the result. This whole cycle repeats billions of times every second in a modern CPU. Let's simulate a simple instruction. DDR1 R2. This instruction adds the value stored in register R2 to the value in register R1. If R1 initially holds the value 4 and R2 holds the value 6, after the instruction is executed, the new value of R1 will be 10. Processors also use different modes of operation, which define their privilege level and control. There is user mode, which is restricted and does not allow direct hardware access, making it safe for running applications. Then there is kernel mode, which has full access and is used by the operating system. Modern operating systems typically use protected mode, which supports multitasking and memory protection. The oldest mode is real mode, which was used by early PCs and has no memory protection. These modes are critical for security, and stability. In user mode, programs are effectively sandboxed so they can't crash your system. Kernel mode is where system calls, drivers, and other OS components operate. The use of modes helps protect memory and prevent the entire system from crashing. Now, let's talk about how the CPU manages data using registers and flags. CPU registers are small, high-speed storage areas located inside the CPU itself. They are used to store temporary data, point to specific memory addresses, and control the flow of instructions. Some common examples are the EAX register for arithmetic, the ESP register, which serves as the stack pointer, and the EIP register, the instruction pointer. Alongside registers, we have flags, which are single-bit values that represent the CPU's status after an operation has been performed. Flags help the CPU make decisions, especially for branching and comparisons. Some common flags are the ZF or zero flag, which shows if a result was zero, the SF or sign flag, which shows if a result was negative, the CF or carry flag for when a carry occurred, and the OF or overflow flag for when an overflow occurred. For instance, if you perform the operation 5 plus negative 5, the result is 0, and the 0 flag is set to 1 for true. If you calculate 2 plus 3, the result is 5, so the 0 flag is set to 0. And for false, these flags are what guide conditional jumps and branching within assembly code. Finally, let's look at the floating point unit, or FPU. This is a dedicated part of the CPU that handles mathematical calculations with decimal or non-integer numbers. It is very important for scientific, graphics, financial, and AI computations. The FPU uses the IEEE 754 standard to represent these floating point numbers in binary format. It can perform arithmetic with decimals like 1.2, 5 plus 2.5, as well as advanced math like calculating a square root or trigonometric functions like sine and cosine. The FPU is what allows CPS to perform these kinds of real number calculations both efficiently and accurately.